Hello again, friends. Welcome to my home, and we are going over the first derivatives test. This is the third page of 6 problems. So we have this one, where a particle's position is defined by S. This is something you'll see rather commonly, where position they use the letter S for position. This is a physics kind of thing. Not sure why, it just is. Equals negative 4.9 x squared plus 17x plus 4, and asks you to find the acceleration at t equals 4. So acceleration, there's a hierarchy of things where we start with just if we have a function that tells us the position of a particle, taking the derivative of the position in terms of time gets us to the velocity of a particle, right? And if we take the derivative in terms of time of the velocity of a particle, that gets us the acceleration. So we are interested in the acceleration of this, which is the second derivative of the position function. So we start off by taking the derivative once to get the velocity of the particle, and that 2 times negative 4.9, that's negative 9.8 x. Oh, that's something I should change here. These should be t's, not x's. Plus 17t plus nothing. So that gives us our velocity. Then we take the derivative once more. The acceleration in terms of time is equal to, well, just negative 9.8. And everything else goes away. So it doesn't matter that t happens to be 4 here. The acceleration is always negative 9.8. So this is your ultimate answer. Great. Now we have this. If y is 3 over 2x squared, find the second derivative of y in terms of x. This is one where it helps to not use the quotient rule, but instead change this to 3 halves times x to the negative second. And then we can take the derivative of that much easier because this is just a constant multiplier. So when we take the derivative the first time, the constant multiplier stays there. We use the power rule, so that becomes negative 2 times 3 halves x to the negative third, or negative 3x to the negative third. Then when we take the derivative the second time, again, we just use the power rule. That becomes 9x to the negative fourth. That's it. If you use the quotient rule, you'll notice that we get 2x squared times the derivative of 3 is just 0, minus 3 times the derivative of the bottom, 4x. Which that cancels out because it's 0. You get negative 12x over 4x to the fourth. So I don't recommend using the quotient rule here because it's obviously much easier. This is much easier. But if you happen to use the quotient rule, that's fine. You just need to, when you do it, take a break and simplify this, right? Rather than just plowing on and using quotient rule again, we see how there's a factor of x in the numerator, factor of x in the denominator. We can reduce that. Again, also 12 divided by 4. That is a thing. So we just get negative 3 over x to the third. Suspiciously the exact same thing as there. But yeah, and then once you're here, this is much simpler to use the quotient rule on than this. So when you use the quotient rule here, you again get something like x to the third times 0 minus plus 3 times 3x squared. x to the fourth. Or sorry, x to the fourth. This, of course, I've been writing behind my. In any case, doesn't actually matter because this is easier. Do it this way. Don't do it this way. Moving on. This is a straightforward limit problem. We want the limit as x goes to 2 of 3x plus 4. There's no complications here. Like, there's no variable in the denominator. This is a straightforward linear function, so the way of evaluating this limit is to just plug it in. You get 3 times 2 plus 4, which is 6 plus 4, which is 10. This one's a little bit more complicated. So let's read it out. What value of k will make the function f of x equals, and this is a piecewise defined function, where most of it is x squared plus 6x plus 8 over x plus 2. I say most of it because the only case where it isn't this is defined as some constant k when x is negative 2. Why did I pick out x is negative 2? Well, what happens when x is negative 2 in this one? You get negative 2 squared plus 6 times negative 2 plus 8 over negative 2 plus 2. That becomes 4 minus 12 plus 8 over 0, which is just 0 over 0. This is called an indeterminate form. We're going to get a lot more into indeterminate forms sometime. I don't know when. We'll get there. But for right now, when you see an indeterminate form, that means, oh, there's usually an avenue using algebra to make this simpler. And in fact, there is. If we go back to our original definition here, this quadratic, can be factored into x plus 2 times x plus 4. And then as long as x is not equal to negative 2, you can cancel this out. It's defined as x plus 4 basically everywhere. And so when you sub in x equals negative 2, negative 2 plus 4 equals 2. So that should be our k to make it continuous. Because that way the limit as x goes to negative 2 is exactly equal to the value when x is negative 2. Now, if dy dx equals 5 times x plus 4 times x minus 3 to the 6th times x plus 2, for what values of x does y have a local minimum? So this, they give you dy dx. This is not our y, though we are asking questions about y. This is the derivative of y. And if we were wondering about local minimum, knowing the derivative, two things need to happen for a local minimum. The derivative has to equal 0. And at that point, it has to go from decreasing, so the derivative is negative, to increasing, the derivative is positive. You could also say that for a local minimum, the second derivative has to be positive, so greater than 0, because that way it'll be concave up. I'm sure it says the local minimum. I'm sure none of you really want to take the derivative of this expression. It is deliberately kind of nasty looking so that you don't take the derivative and think about it in other ways, but certainly you can take the derivative of this and find where that is, whether or not that is positive. But anyways, let's look at this. This expression is equal to 0 at 3 spots. When x equals negative 4, when x equals 3, and when x equals negative 2. So if we kind of think about that on a number line, we have negative 4, we have -2, and we have 3. And we can think to ourselves, kind of isolate this and just think about the sign of the function in the regions where it's not 0. Some people think about, when you're doing this analysis, some people start over on this side, some people start on this side. It's helpful to start on one side and just move continuously. So let's look at this. We have, if we are less than -4, then all of these factors are going to be negative. So we have a positive number up front times a negative number times a negative number to the 6th power. Well, if it's to an even power, it has to be positive. So we get negative times positive times negative, which means that in this region, the derivative has to be positive. Moving on. Once you cross over this line, this factor, x plus 4, switches sign. It switches from negative to positive at -4. So now, in this region, we have a situation where it's a positive factor times another positive factor times a negative factor. So this must have switched to negative. Crossing over the -2, that switches this factor. So that must be positive, positive, positive. That's positive, and this was always positive, so it stays positive. All right, we are looking for, so we've done our analysis. It is time to look at what we have and see what we want. We want a local minimum, so we want from negative to positive. There's only one spot where it does that at x equals -2. So that'll be our answer. Finally, for this page, this is another one with a hand-drawn element, so I couldn't copy it here. The figure below shows the graph of f prime. There is no figure below. I'll just draw in a couple example graphs. The derivative of the function f on an open interval from -5 to 5. If f prime has 3 zeros on this interval, how many relative maxima does it have? If I remember correctly, I think this one looked something like 1, 2. So you have 1, 2, 3 zeros. So this is important, especially in something where it's a figure. It says that you have 3 zeros, so there's something with 3 zeros. This is, again, a graph of f prime. This is not actually f. So you shouldn't look and see, oh, hey, there is one relative maximum, right? That is a relative maxima of f prime, not of f. If we're looking for the original function, relative maxima are where the function goes from increasing to decreasing. So that means our derivative function, if this is our f prime, has to go from positive to negative. And there is, in this case, one situation where it does that, positive to negative. So in this particular graph, you have one relative maximum. Some other graphs with 3 zeros you might have. If you had something like this, if we're looking for relative maxima, again, it goes from positive derivative to negative derivative. That's a spot, and there are no other spots. If we flipped it, there'd be 2 relative maxima, but as it is. So if we had something like this, 1, 2, 3, there'd be this spot, there'd be 2 relative maxima. But there aren't. So these are some of the options you can have. It obviously depends on whatever picture you are confronted with, but keep note, the most important part is that you are given f prime, the derivative of f, not f itself. That should do it for the third part. Thanks for stopping by.